Bismillahirrahmanirrahim. Welcome to the third part of the eigenvalues and eigenvector topics. Last time we defined the eigenvalue is just a scalar or constant that satisfies the linear equation or system A times k equal to lambda k, where k is non-zero vector. We say that lambda is an eigenvalue of the matrix A if there is a non-zero vector k such that A k equal to lambda k. So this is lambda is an eigenvalue. In the last time we gave some example how to find the eigenvalue and the eigenvector. To find the eigenvalue, we have to find the determinant of A minus lambda I. This is to find lambda, we have to find the determinant of the matrix A minus lambda I, make it equal to 0 and solve it for the eigenvalue. For today, we are going to speak about the triangular and diagonal matrices, and also we have one theorem say that let A be n by n matrix. Then the number lambda equal to 0 is an eigenvalue of the matrix A if and only if A is singular. A is singular means the determinant of A equal to 0. The determinant of A is equal to 0, then that lambda, which is equal to 0, is an eigenvalue of the given matrix A. This is because we have determinant of A is equal to the product of the eigenvalue. That's lambda 1 times lambda 2 up to lambda n. This is equal to the determinant. It's just the multiplication with the eigenvalues. So if the determinant equal to 0 means there is one lambda equal to 0, or the lambda equal to 0 is one of the eigenvalues. For the diagonal and upper diagonal matrices, and diagonal or upper triangular and lower triangular. For the diagonal or upper triangular or lower triangular, we have three types. Say that A is triangle or diagonal means we have entries non-equal to 0 in the main diagonal and 0 everywhere. Or we have B upper triangular, that will be 0 in the lower part and non-zero in the upper part, or C, non-zero entries and 0 in the upper part of the matrices. So the A is diagonal, B is upper triangular, and C is lower triangular. This is diagonal. This is upper triangular. And this is lower triangular. The eigenvalues for these type of matrices. The eigenvalues of an upper triangular or lower triangular or the diagonal and diagonal. Matrix are the main diagonal entries. So this is the main thing, the main diagonal entries. If we have diagonal matrix or upper triangular or lower triangular, the eigenvalues will be the main diagonal entries. For example, let's find eigenvalues and eigenvectors. Of the matrix A given by, say, 4, 8, 0, minus 5. This is upper triangular matrix. You can see. So this is upper triangular matrix. The main diagonal element are 4 and minus 5. So these are the eigenvalues. So the eigenvalues are lambda equal to 4 and lambda equal to minus 5. So if you have upper triangular or lower triangular, the eigenvalues will be the main diagonal entries. Now we have the eigenvalues. Let's find the eigenvectors. For lambda equal to 4, a minus lambda I, or minus 4, say minus 4i, is equal to 0, 8, 0, minus 9. So the eigenvectors will be to find the eigenvector, I will have 0, 8 minus 9 multiplied by k1, k2 equal to 0. This will give me the system 8 k2 equal to 0 or minus 9 k2 equal to 0. This means that k2 equal to 0. But nothing mentioned about k1. So k1 can be any value. So the eigenvector will be capital K, which is equal to k1, k2 is equal to k1 and k2 is equal to 0. Or I can write this as k1 multiplied by 1 and 0. So for any value of k1, I will have eigenvectors. So I can take k1, let k1 equal to 1. So the k, which is equal to 1 and 0, is an eigenvector, or is the eigenvector. Corresponding to lambda equal to 4. Now for the second one, for lambda equal to minus 5. I will have a plus 5i k equal to 0. Now 5 plus 5a will be 9, 8, 0, 0 multiplied by k1, k2 equal to 0. This will give me the system or equation 9k1 plus 8k2 equal to 0. And from this one, we can find 9k1 equal to minus 8k2 or k2 equal to minus 9 over 8k1. So the eigenvector k, which is equal to k1, k2 is equal to k1 and k2 is minus 9 over 8k1. I can take k1 as a common factor. I will have 1 and minus 9 over 8. So k, which is equal to 1 and minus 9 over 8, I can take k1 equal to 1, is the eigenvector corresponding to the eigenvalue lambda equal to minus 5. So this is the idea. If I have upper diagonal or lower diagonal or diagonal matrix, then the main diagonal entries are the eigenvalues, and we can find the eigenvectors for each one of them. Let's have another example. A equal to, say, 1, 0, 0, 2, 5, 0, and 3, 6, and minus 7. Again, this is upper triangular matrix. So the main diagonal entries 1, 5, minus 5 will be the eigenvalues. Lambda 1 equal to 1, lambda 2 equal to 5, and lambda 3 equal to minus 7. I have 3 eigenvalues, so we must have 3 eigenvectors. For lambda equal to 1, a minus 1i k equal to 0. That will be 0, 0, 0. We subtract 1 from the main diagonal. 2, 4, 0, and 3, 6 minus 8. Just subtract minus 1 from each one of the main diagonal for lambda equal to 1. Multiplied by k1, k2, and k3 equal to 0. This will give me the system. 2 k 2 plus 3k 3 equal to 0. And it will be 4k 2 plus 6k 3 equal to 0, or minus 8 k 3 equal to 0. From the last equation, k3 equal to 0. Also, this implies that k2 equal to 0 also. If k3 equal to 0, then we will get also k2 equal to 0. And we don't have k1 in this system. It is not mentioned there. It means that I can choose k1 to be any value. So the eigenvector or should I say, okay, the eigenvector for this one, k, which is given by k1, k2, and k3 is equal to k1, k2 is 0, and k3 equal to 0. So I can take k1 out. It will be 1, 0, 0. Now for any value of k, I will have the eigenvector. If we let or choose k1 to be 1, and we have to be careful that k1 can't be 0, because from the definition, the eigenvector should be non-zero vector. So I cannot take k1 equal to 0. I have to take k1 not equal to 0, any number not equal to 0. Then k, which is equal to 1, 0, 0, is the eigenvector corresponding to lambda equal to 1. Let's take the second eigenvalue. Now for lambda equal to 5. A minus 5i. K equal to 0. I will have minus 4, 0, 0. Just subtract 5 from the main diagonal entry. 2, 0, 0, 3, 6, minus 12. Equal to 0. This will give me the system minus 4k1 plus 2k2 plus 3k3 equal to 0. And will give me 6k3 equal to 0 and minus 12k3 equal to 0. From this system, I will get k3 equal to 0. So we'll have minus 4k1 plus 2k2 equal to 0. This will give me 2k2 equal to 4k1 or k2 equal to 2k1. So the eigenvector k, which is equal to k1, k2, k3 is equal to k1, k2 is equal to 2, k1 and k3 is equal to 0. So take k1 as a common factor. I'll have 1, 2, and 0. So the k equal to 1, 2, and 0 is the eigenvector. Lambda equal to 5. Last one, lambda equal to minus 7. Then a plus 7i k equal to 0. That will be 8, 0, 0, 2, 12, 0, and 3, 6, 0 multiplied by k1, k2, k3 equal to 0. And this system will be 8k1 plus 2k2 plus 3k3 equal to 0 and 12k2 plus 6k3 equal to 0 and nothing mentioned about the third row. It is all of it equal to 0. So I have to solve this one. From the second equation, we'll have 6k3 equal to minus 12k2 or k3 equal to minus 2k2. This is the first one. So I can replace k3 in the first equation by minus 2k2. This is the first equation. From the first equation, we'll have a k1 plus 2k2 plus 3 multiplied by minus 2k2 equal to 0. Replace k3 by minus 2. So it is 8k1. 3 minus 2 is minus 6 plus 2. It will be minus 4k2 equal to 0. So k2 will be 2k1. And from this one, this will give me k3, which is equal to minus 2k2 is equal to minus 2 multiplied by 2k1. That will be minus 4k1. So the eigenvector k, which is equal to k1, k2, and k3 is equal to k1, k2 equal to 2, k1, and k3 is minus 4k3. we can take K1 as a common factor. It will be 1, 2, and minus 4. So if K1 equal to 0, K equal to 1, 2, minus 4 for K1 equal to 1 is the eigenvector corresponding to lambda equal to minus 7. So these are the eigenvectors for the upper triangular matrix. The main idea is that the main diagonal entries are the eigenvalues, and for each one we can find the eigenvector. Yes. Last remark in this topic. The eigenvectors are linearly independent. The eigenvectors for any matrix are linearly independent. Means that if we form a matrix of the eigenvectors, the determinant is not equal to 0, or that matrix is non-singular. This is the meaning of the linearly independent. So that's it for this lecture. We found the eigenvalues and we found the eigenvector for each one for the upper diagonal. Same thing we can apply it for the lower diagonal or for the lower triangular or diagonal matrix. We have upper triangular, lower triangular, and diagonal matrix. For each one of these, the main diagonal entries are the eigenvalues.